Oh, my mic was off there. Hello. Hey. Hey. How's it going? Let me turn this down just a little bit. Just a skosh. Let me also... so we're not in the void. Oh. I was a little worried there that we were gonna get something. No, this is fine. That is not what we need. Hey. Hi. Hope you're doing well. I don't know, I'm just gonna work on some EE stuff, and then I don't know, maybe we'll do path coordinates for dynamics, because okay, if I don't have dynamics, I might not be able to do that much dynamics, because our problem set is for a little bit farther out, so they just announced an actual email for the Teamsters and Professor Strike. That's crazy. Anyway, let me pull this up. Where do I need to go? Oh yeah, McGraw Hill, I think it's called. Yeah. I love paying $100 for a textbook. Hi. How's it going? Let's see, 500 B-Way? That's probably not how you pronounce that. 500, I'm gonna call it 500. Or like B-Way, like Broadway? Or like... I don't know what else B-Way. Oh, Subway. Oh, it's elite speak. Oh, I get it. Good, how am I? I'm okay. I was like, kind of going through it in my classes today. I don't know why, but my eyes are super tired. And I was like, I felt really bad because I think I just had like something in my eye, like for a long time. So I like couldn't, but I felt bad because my professors, I was like, I swear I'm not falling asleep in your class. Yeah, unfortunately this is not interesting electrical engineering. This is like busy work, but we do that on stream. What classes do I have? What did I have? I had my mechanics and materials. That's a fun one. That's my 7 a.m. And then I had my circuit theory and what was it called? What was the other thing called? Dynamics. I don't know, I just couldn't remember dynamics. I love dynamics. Dynamics is really cool. It's very fun. Okay. I don't even know if I need to like screenshot this because it's so simple that I don't really need to screenshot it, but you know, so you guys can see it. Oh, that sounds fun. Yeah, it's pretty fun. I like my mechanics and materials I'm kind of divided on because I like the content a lot, but the way the professor teaches it is a little boring, or like not boring. It's very example based instead of like theory, which, you know, is a little bit less fun. I like theory more. Okay, we need to find power. Power is, what is power? Power is IV? No, what's power? It is... Oh, that's not it. Oh, yeah, it's a VI, I do. Yeah, or what is it? I squared R is also the other one. Can remember some things. Okay, so this... Wait, this is so easy. We just multiply two numbers? Are you kidding me? Oh my god. This is the crossover people want. Oh, this is awful. It's multiplying two numbers together and they give you both the numbers. Oh. This is why I want to just... I only have like a tiny amount of these to do, so I can just get through it. Oh wait, that was not correct. Okay, 22.5. I'll round it. Awesome. Okay, this might be like really this might be like we do these in 5 minutes. Oh no. Okay. And the power delivered by the source. The power delivered by the 9 volt. It's just multiplying two numbers again. Why is this a 200 level class? Why do I need to take physics 3 as a prereq to get into this class? Yes! The multiply two numbers together class. Oh no. Oh no. Okay. Well, at least it's not hard. 39.5. I don't know how many sig figs they want. It's okay. We'll... Okay, thank God. This is slightly more in-depth. Not that much more in-depth. Looks like we're gonna be doing dynamics today for sure, folks. Let's see. Okay. Oops. Hey, Alfie. How's it going? This is so goofy to me. I can't believe... Okay. So, the power absorbed by the R4... if we want to do that, we can do power equals IV, sort of our base little thing, and then we have two options. We have V equals IR if we have current and we want to get rid of voltage, or we can go for the other option is if we have if we replace current with this bad boy. So we get V squared over R. So V1 equals 3.6, so we'll just square that and then divide it. Pretty easy. Oh, let me pull this on my second monitor one sec. Me being a streamer, there we go. Turn up brightness on this. Wait, what? Okay, there. I should probably get a calculator. That would maybe make my life marginally easier. Okay, wait, these ones might be a little bit different. Let's see. So, let me just check this. We have the voltage and we have the resistance. Yeah, that should be fine. And they give us all of the voltages. Oh, they don't give us the... They don't give us the resistors. Let me do that then. Oh no, your sleep is hacked. Hacked. Oh. I love reading with my astigmatism. Letters that are round are hard. I had some fun chats earlier today. That's cool. Okay, we actually have to do some stuff, I think. Luckily. Or do we? How much stuff? Can I get away? Let's see, power absorbed by R4. So the current is going to be 2A here. We do have voltage. Oh, I don't even need to do this. What am I... This is just going to be... Oh, we'll just do A. It's going to be the 2 amps times power. Let's do... They're speedrunning Diablo? That's awesome. R4 is 19 volts. The power delivered by the current source is... Okay. So if V3 plus V4 equals V5. So that means that... Oh, I don't have a V3, but we can find V3. That's going to equal 10 volts plus 3.6 volts. Oh wait, that's minus 9 volts. Feeling good. That's good. Let me think about this. If V4 is not 10... I was wondering what level of math I do. You're doing a different major. The math I've seen you do seem similar to what I do the first year math degree in the UK, a bit more advanced. Maybe do the second equivalent of my second year math. So the way that I kind of like to think about it, or at least for my school, depending on what university you go to, you may get more or less math in an engineering degree. But my school is a very technical focused school. So the way that they sort of think about math is we take basic math courses, and I took more math than most people did in high school. We take some basic math courses, but a lot of the times we learn the applied version of the math, not the theory. So like, for example, we take a version of like differential equations, you know, we have to work with differential equations, but it's more sort of, I mean, some people would call it like tailored to an engineer, but it's kind of like just dumbed down, and we don't really learn the theory so much as like, this is how to just brute force your way through solving things. So yeah, I would say first year math in a degree, or maybe some higher level stuff, but it is not like none of the theoretical stuff. That's the best way I can describe it. And I think it's like, it's interesting because I think there's a time and place sort of for having more of a sort of friendly relationship with certain types of math, being able to use them applied in more informal ways. But I think it really is kind of detrimental if you don't, like, I wish I could study more math. I probably will try to take a math minor because it's not that many extra classes for me. Yeah, that's the best way I can describe it. Okay, I might actually have to do a little bit more work on this. Let me see, so this is, we'll just call this 0 volts. So we step up 10. Oh, you only had an 8 a.m., so that, oh, that's nice. I would, I like my 12 p.m.s. I like my 12 to 2. My 12 to 2 is great. It's the best time period. Just grab my calculator. Not that I can't do 10 minus 3.6 in my head, but, it's gonna be negative over there. Oh, wait. Is that okay? Wait, that might not be okay. Let me think. If that's 19, oh, we can kind of backwards out, because it's not going to be 0 volts there. Okay, this is a little bit more complicated. So 10 minus 3.6 minus 9, that gets us at negative 2.6, and we step down over this one as well. So we're gonna minus 19. So that down here is negative 21.6, and then we go from the 10 minus 3.6 minus 9, which is negative 2.6 here. 2.6. I hate waking up early, but I'm able to get my classes out of the way quicker. Yeah, that's real. That's real and true. Plus 21.6. Okay, so that's 19. Oh. Wait, what? That seems not right. I mean, I guess... Oh, wait, no, there's gonna be something in between here. Lol, there's gotta be another thing in between here. But... This is the negative 21.6. Am I just being real goofy? Let me see. So that's that loop, and then that loop over there. Maybe I don't know why I stopped doing this way. Because it was a negative number? It's okay, voltage can be negative. Silly Damert. Negative 2.6. Does that make sense? It would have to be a positive 2.6, I think, because it has to be 0. Yes, maybe, no. Yeah. I should probably do this. Minus V3 equals 0. Wait, no, that doesn't fix my... Wait a second. I'm thinking. It gave us these polarities. It's... it should be positive. Okay, we ball. Positive. It should be positive. 2.6, because it has to be 0. And then, okay, then we can just do the other one. So the power absorbed by R4 is going to be the, this, which is, what is that? That's 2 times 19, 38. And then this one is the power delivered by the current source. So we do V3 plus V4. So that's 2.6 and minus 21. well, if we go around from here, so we say over this way, 21.6, 21.6, and then this way we're gonna add, let's keep my sign convention the same, even though I switched it between problems. Don't worry about it. Don't worry about it. Current, or we'll say like VC, and then minus, that would be a minus. It's fine. Minus, what do we say? Almost 2.6. So VC equals 21.6 minus. Wait, okay, 19. Sure, whatever. That sounds vaguely right. Well, but it's this times m2. Wait, it's the same. Okay. That's a watt also. Oh, it's already scuffed. I'm not sure how I feel about that. I feel like that's not right. That seems kind of not right is the thing. I mean, for R3, the current's gonna split, so the current won't be 2. Like, that feels kind of weird. I guess I could check the outer loop. So it would be 10. Let's try that. So if we're going from negative to positive, oh god, let me turn my mouse. If we're going up, okay, let me put it more on center screen for you guys. That was my negative direction. So we'll say negative 10 plus 3.6 plus 2.6. I have another plus 21.6, and then in this case it would be positive negative, right? So that's definitely not 0. Definitely not 0 is the thing. I probably want to do that. I probably want to do that one, huh? Because it's only one variable there. That seems more right. That seems more right. In that case, though, it would be like, if that was 0, it would have to be... I'm not sure how I feel about these polarities. I don't know if these polarities are right or not. If I know they're not right, then that would make a lot more sense. Because they can't all be going this... Wait, no, this one is the negative. That seems weird. Oh wait, it's also not 21.6, it's 19. Not that makes a big difference. Let's just casually not worry about that. Okay, that's fine. We're chilling. We're chilling. It's fine. It's fine. Don't worry about it. Don't worry about it. Probably just gonna like erase everything and redo it. That's normally what I do. Okay. Determine the power absorbed by the resistor R equals 5 ohms. Okay. We need 2 things. We could do voltage or current, but we might as well just do current because so REQ is going to equal 20 ohms. That one's pretty easy. And then I equals V over R, so 20 volts over 20 ohms, which is 1 amp. And then power equals IV, but it's the other one too. What is it? It's the one with R squared in it. If we have resistance and we have current, I squared R. I squared R. Yeah, just checking. So 1 squared times the resistance is 5 ohms equals 5 watts. Perfect. Beautiful. Life is absolutely gorgeous. I love everything. I love circuits. I love frolicking around in the electricity. Use KCL to determine... Okay, sure. Use Kirchhoff. Kirchhoff? I've heard some people say Kirchhoff and some people say Kirchhoff. I don't know which one it is. I should probably look it up. That'd be, I feel like that's like pretty important to like just know the name of the guy who did everything. Let's see, is it Kerr? Let me get a pronunciation on that. Let's see. Okay, I cannot pronounce. I cannot pronounce this. I don't know how to pronounce that one. That one's I think it's Kirchhoff. I think it's also Kirchhoff, but my current professor keeps calling him Kirchhoff, and I'm like, But then again, people mispronounce phi, like phi, every single lecture. See, I literally called it phi. It's pronounced phi. This thing. Phi. Rhymes with pi. Oops, that's not it. Okay. Determine I1 and I2. Alright. Okay, so we just add them all up. So for A, I don't know, let's do A first. I've never heard it called phi. Because people read it like this, and for some reason they think that equals phi. like phi, fi, fo, fum. But like it's like pi, it rhymes with like phi. I don't know, people definitely have gotten that one wrong, at least in my classes. Which, you know, maybe not a good sign, but what can you do? Okay, so IB equals IA plus IC. And then, we have another one, plus IB plus, woof, IB plus I1. Equals IA plus IC, and then over here, for A, and then for B, we've got, going into it, we've got IE, and then plus ID equals I1 plus I2. At least it's not a 7 a.m. Yeah, my 7 a.m. is pretty rough. I get up before the sun is up, which is, you know, normally it wouldn't happen that way if it were not winter, but, you know, it's winter and it's daylight savings. Makes me feel kind of cool, though. Like, sneaky. I know somebody in that class, so we suffer together. Okay. Science are my I think this set of classes that I'm taking right now has the most, like, what's the word? The most, random assignment of signs and disorganized way of dealing with signs consistently. Like, for example, in like material mechanics, this is something we did in statics, but like everything is always assumed to be in tension, even if you have like, okay, hey guys, like, oh, I'm gonna put like a load on this beam that's very long and it's gonna have a force P, right? And I'm gonna assume, let's like take the bottom half of this to do like a free body diagram of to find the internal stress. It's like, okay, well, so if the force goes up and then you just get F equals negative P, it's like, can we just draw the free body diagram in compression, please? Please can we draw it in compression? This is what this feels like. Why is the current negative? Why are you drawing it negative there? Does it mean that this arrow is incorrect? Like, I don't know what that means. To me, if it's a negative number, it means this arrow is incorrect. Not this arrow is going backwards. But I have a feeling it's this arrow is going backwards. I don't know. But it's not that, because look, IA is 3.8 amps and IC is 3.4 and they're going in different directions. So IB must be going the wrong way. Okay, fine, negative IB then. Or I'll just put in a value for IB that's negative. I don't know why you would, like, this is just confusing for no reason. I feel like this sucks. But maybe it doesn't. Maybe it's just me. So negative 3.6 amps plus II. And then we have this one, which is plus 3.4 amps, which is nice. We can just put everything together. That is how I feel Mario music. 10.8. Also feeling pretty happy that I got that. I did this one first instead of the other one. Okay, so this one is -8. I'm just gonna go with this, and then 9.2, and then 10.8. Cool. This one is a little bit weirder. So 9.2 minus 8 minus 10.8. Again, don't know how you do that to yourself, but I mean, go off as long as you can understand it. Alright, well, that is all of the electro that I have to do. It was 5 problems. That was it. Took not even half an hour. Okay. Well, that's that. I could do... what shall I do? What shall I do? I kind of want to do dynamics. I kind of really want to do dynamics. Me looking at dynamics, be like, haha. Oh wait, that's my programming course. Why did I click on that? Dynamics. I could do... I mean, I could do... No, you know what? I should do a mechanics and materials. Let's do a little mechanics and materials. Why not? It's a fun. I could do an axial indeterminate problem. Wait, no, I should do a determinate problem. Oh god, they're so small. Okay, well, that's fine. Let me, like, see which ones he said to not do real quick. He was like, guys, you don't need to do these ones because they kind of suck. And I was like, why do you put them up on your site then if they are not that good? But, you know, you do. He said, feel free to skip problems 2, 5, and 8. Oh, 8 and 9. I lied. Those are the practice problems. Okay. Don't do 8 and 9. We might have done them in class. That might be why. Oh no. They're just like a... What is that? It's a tie rod. I can see why he has to... Oh, and one of them is just a bad statics problem. I remember him talking about that. Let's do 3. 3 is best number. Arguably. Okay. Alright. So, just a little preface. Mechanics has some materials. It's a class about stress and strain. So it's like doing statics, but internally, essentially. And a lot of it is about saying, okay, well, we have a load that's placed on this thing. What are the material properties of this thing? Whatever it is, this beam. Usually it's, I mean, for these problems, it's an axial model. So it's like a long, thin beam that we make a lot of assumptions about. And we're trying to figure out how much it deforms. Like stretching or compressing. So in terms of this one, so the same cross-section and material properties. So our basic equation that we have for this is we have a delta. The delta equals, well, it's like proportional to, we have, it goes up as the load that we put on it goes up. More deformation. As the bar gets longer, it deforms more. As the elasticity of the material goes down, which means that it's more elastic, so something like a rubber band would have a very low elasticity, versus something like steel would have a very high elasticity. As the elasticity goes down, our deformation goes up, and then as our area decreases, we have more deformation as well. So that's our kind of equation that we use for everything. And that's our constant one. There's an integral version of it as well, if you have a shape that's not a beam. Yeah, let's see. So we have a load shown, there's loads on it, and we have a uniform temperature increase, which is another equation. That's, there's a deformation sort of temperature subscript, and then we have an alpha, which is a material property about how much it deforms, and then it's based off of the temperature difference and the length of the material. Again, which kind of makes sense. If we increase the temperature, it'll deform more, right? It'll expand more or shrink more. and then with the length, it's kind of the same thing as like a thermal mass, right? So we want to find the z displacement at C and the stress at point P. So we don't have to worry about D too much, that means, because we're going to be doing our analysis on this half of the thing, I think. Is that a lie? We might not have to worry about A. No, we might have to worry about both of them. We're gonna go through it. The only thing I'm thinking about is if there's a reaction force here, then I don't want to deal with that. Yeah, let's just jump into it. Okay, so we tend to do 4 steps, 3 steps, 4 steps. So we start with equilibrium. So we're trying to find the internal forces. We're trying to essentially find this part, because these loads right here, these are like if you took like your hand and then you grabbed it and you pulled your hand to the right. So these aren't the internal forces, even though they're shown on the thing as they're shown on it. It's like this is the same thing as this. It's an external load. So we have to do some free body diagrams. Let's do the one for D. So here's D, and we have our 3 kilonewtons. So our force D, is going to equal 3 kilonewtons. It's pretty simple. And it looks like we're trying to find the stress at point P, so we're definitely going to need to do an internal force here. So we just take the whole thing, or not the whole thing, this much of the thing. And we say, okay, well there's a 3 kilonewton at the end there, there's a 5 kilonewton here. Let's see, if 5 is going this way and 3 is going this way, we gotta do another force C. Force C equals 2 kilonewtons. And that means that this beam is in tension, whereas this one, this part of this beam is in compression, this member. So we got that. Now, okay, there's 2 ways I could do this. So we're trying to find the displacement at C. Yeah, I don't need D, but that's okay. Oh, I forgot. I'm gonna cut it. I'm gonna cut it in between A and B, so we don't have to worry about that reaction force. I was right. We don't need to have D. That's okay. You know, you live and you learn. No harm in doing D. It really wasn't that much further. Okay, and then we have our FA here, or FB, I guess, using our naming convention. So we made a cut here, we made a cut here, and we made a cut there. So our FB is going to equal, what have we got? Let's see, there's 9 that way, so it's going to be 6 kilonewtons. Alright, so we have all our equilibriums. Those are all our internal forces. Now we have to do our constitutive. It's something that starts with const, and that's all he abbreviates. So that's what we're gonna go with. This is essentially like our forces, and then this is our deformation, and then we do kinetics to put them together. So this is where we're going to say, so our deformation at point A, and I'm looking ahead, or at point B, I guess. Looking ahead to say, I know something about the total deformation, so we're going to start from this side and only do these two, because we actually don't need the deformation over there. So we have our rho L over EA, and those values are going to be whatever they are for B. And we're going to add our temperature delta TL for B as well. And then we do the same thing for C. So PL over EA for C plus for C. Nice. Cool. Awesome. And then for our kinetics, which is relating the two, we want to relate these two displacements somehow to something that we can find. In this case, it's fine. Sometimes you'll be given a displacement and asked to find like a load or something. So we're going to say displacement at point C, which I guess is not a great subscript. Let's just say C total equals the delta B plus the displacement of the delta C part. So we just add them together, and that'll give us C. And then for our is asking for stress? Yeah. For our stress is just force over area. It's a pressure. So we're gonna take the force at C, which is just this, and then put it over the area of the thing, I think. We do have to be careful about units. We put everything in meters, I guess. Oh, that sucks. Oh, who wants to put everything in meters? Ew, it's in millimeters. That's one of the assumptions we have to make, though, is that the deformations are very small compared to the length of the beam. So the length of the beam is like, what? It's 3.75 meters compared to like a deflection, and it's got a very small diameter as well. Or, I mean, area and diameter. So these deflections are going to be very, very, very small. And our elasticity is 200 gigapascals, which is quite large. So, all right, delta B. So, okay, our force at delta B is our 3 kilonewtons. And our length for delta B is 1 meter. So we do this chunk. It's a little unintuitive, but that's the length of it. No, it's not the, wait, is that the, wait. My brain. No, that's the length of it, I'm pretty sure. It might not be right. Don't listen to me. I'm just a cat boy on the internet. Giga is 10 to the 9th, right? Okay, if I type in giga, it comes up with giga chat. I don't need to know that. Power of 10. Yeah, 10 to the 9th. Nice. And then our area, which is going to be very, very teeny weeny. So we have millimeters squared, which means that we need to do 1 over 1,000 millimeters, and then that squared. Then plus the 16 times 10 to the negative 6th times the temperature change, which is 40 degrees Celsius. And then the length as well, so 1 meter. That should give us the right thing, question mark. Let me reply to someone real quick. Okay, let's see if this is right. I don't know how I'm gonna see if this is right, actually. Oh wait, I think they have, like, worked out solutions, maybe. Well, if we get it wrong, then I might have done my sectioning wrong, which is entirely possible. I'm also converting the kilonewtons to the proper, just so, you know, no one was worried about that. Okay, divided by 36, whoops, divided by 88, divided by 36, and then we, whoops, we take this and we divide it by 1 divided by 1,000 squared. No. I don't know if that's right. Well, I guess it could be. What is that? 1, 2, 3, yeah, 2.7 millimeters for this first part of it. Now see, if we got it wrong, we would be getting this wrong, which is very, very small in the big picture. Well, actually, it wouldn't be that small. 2.7 millimeters. And then we have the temperature change, which is 16 times 10 times 40, 10 to the negative 6, and then times 40, which is 6.4 millimeters. So overall, this equals 0, not 0, 9.28 millimeters change, which, you know, is not large for something that's 3 meters long, but it still feels a little weird. I think the magnitude is probably right though. Probably right. Let's see. Okay, for the other one, can I? Okay, how much longer is C? I would say 1.25 in that case, I think. 1.25, so that would be... I'm just going to take the 2.7 and multiply that by 1.25. And then I'm going to take the other thing and multiply that by 1.25, because the other ones were 1, so that's kind of a nice... times 1.25. And then add that, and that. Okay, so this gives us 11.47 for C. Alright, so we have those, which means that the total deformation is going to be delta C total equals our 9.28 plus this. Let's see. 20.65. And then the sigma would be, or our stress would be, it would be, I think it would just be 2,000 over 36 millimeters squared. We're at 36 millimeters squared. I think. I mean, I could be, you know, wrong, but that's okay. 55.5. Actually, don't know what we measure stress in. It's some sort of force unit. In this case, I guess it would be pounds? No, newtons per millimeter? That's not right. What's it's like a PSI, but like it's a Pascal. Pascal unit, let's see. 1 Newton per meter squared. Okay, so if we change this out, no, if we do that, and then we do times 1 over 1,000 squared. Yeah. This times 1,000 squared is a lot bigger. What is that? 55 million. So 55 megapascals? Or 55.6. That seems right-ish. I say just completely wrong. Let's see. Let's see if it's just like completely wrong. That is not the one I need. I need quiz 3. Oh, solution. Okay. Okay, I was off by a power of 10. But I was correct on the 55.6 somehow? This one I was off by a power of 10. Wait, I might have just like done my units wrong then. Or I might have done my things wrong. Do you know what I mean? You know what I mean. Oh, I'm stretching. I might have done my, whatchamacallit, did I count the number of decimals wrong? I feel like I didn't. I feel like I counted them right. 1, 2, 3. Wait. Millimeters is 3, not 4, right? 1, 2. Okay, yeah, I counted my decimals wrong. Hey, that's great. We got it right then. So it's 2.65. Well, no, 2.0, 2.07? That's not correct, is it? It's like close enough. Hey, close enough is good enough. Yeah, you know what I'm saying. You know what I'm saying. It's close enough. It's close enough. It's like, it's not very close. I don't know why that's not very close. I mean, it could just be because I was doing it on a phone, which is, you know, don't do that. Don't be like me. Let me get my calculator. I gotta grab my calculator at some point. Let me do that. One sec. I don't want to replug all of it in though, to be honest. But we'll see. We'll see if I can get it. Okay, that's a pretty clear win to me. Getting it right first try? My professor today, he was doing this one problem. It was really easy. It was a problem that was like a little bit easier than this. There was no temperature change. And he said, "Hey guys, if anybody can tell me this answer to 2 decimal places right now, I'll give you an A in this class." And I said it like quietly because I had done the problem before he finished it. And he was like, "Oh, time's up." And I was like, I did it. I got it right when he said it. I was so mad that I didn't just like shout it out and have it be like right, and then him be like, "Whoa, what do I do?" He's a funny guy. He's like, "Oh, you guys take stuff too seriously." Okay, so 3,000 times 1, we're all chilling, divided by 300, divided by 10 to the 9th, divided by 36, divided by 1, divided by... A lot of divided bys, sorry about that. E4, yeah, so 2.77 E4. And then we add the 16 times 10 to the negative 6th times 40. And if we add these... 9.17. Oh, 9.17 is 9.8. 9.118. Not the same number. And then the other one was if this times 1.5 and this times 1.5. That was incorrect. My calculator is getting to the point where it kind of just doesn't really like register when I hit values sometimes, especially operators between putting numbers in from my history. And so it's a little bit not great. Okay, so I got 0.01, so I got 1.37 millimeters, or 1.38, I guess. That's weird that it's so off. This I feel like is making my case worse, isn't it? Oh wait, no, it's making it, maybe it's making it better. Is this plus my 9.1 2.29 2.34 wait, no, 2. That's not how rounding works. You can't round a higher one and then be like, oh, it's up for that. It's close. I don't know why it's not the same. Oh, because it's 1.25, not 1.5. Whoopsies. Actually, that would make my case less correct, wouldn't it? He's getting a higher number. I don't know how much he's rounding, though. Let's see. This plus this is that, and that. Sorry, you guys, I can't. This one. Let's just see. How do I add them together? It's the 9.1, yeah. 2065. 26. Got 2.6206. I got 2.065. That seems off. That is off by like a fair amount. Did I do my lengths wrong? I feel like I can't have done my lengths wrong. I don't know. I got the other part right though, so I feel like it might just be some rounding thing he did, or I did, or maybe I got my temperature wrong, or he changed it somewhere. Cause he... Oh, let's see. He did a free body. He did different free... Wait, let me show you guys. I'm gonna stop leaving you in the dark. Okay, so he did different free bodies. Or he did two the same. I did D. You don't really need D. B is that, where I is section number. Why is he doing all three? Oh no, to 2. This is a really weird way of writing this, isn't it, huh? He couldn't just say do section 1 and 2, he had to write sigma I to 1 to 2? At that point you've just written 1 and 2, and you're just making more work for yourself. Okay, but that's right, that's right. Huh, okay, well... kind of right, 2.62, pretty off, but I have no clue how he did this bit, so it's not like I can check my work there. Whoopsies. Okay, I guess I could do another one. Let's see, is there any good ones in here? Is there any fun ones? What if I did this one? This one could be fun. And by fun, I mean, fun, in quotes. Oh, that's a large picture. Nice of him to upload such a large picture. Not used to that. Okay, so bar ABC is rigid and rotates freely about B. The loads consist of a point load and a uniform temperature change in both bars CD and EF. Determine the temperature change. I just started reading this and my brain just turned off. Okay, the point load and the uniform temperature change in CD and EF. So we have to figure out like how much these guys are shrinking to figure out this dude. Determine the temperature change. Oh, determine the temperature change at which points A and E first come into contact. Ooh, okay. That is fascinating. So as the temperature changes, what's going to happen is we are going to start to close this gap over here, but this is going to expand as well. So it's going to sort of speed up that process, I guess. So we can't just say like delta T equals, you know, this delta TL. It's going to be small. It should be smaller than that number. So let's just put that as a, let's like a heart, like without CD, 0.11 inches equals 13.5 times 10 to the negative 6 times delta T times the length, which is 50 inches. Delta T max equals, this is like the worst case scenario, right? If there was no bar. So 0. This divided by 13.5 times 10 to the 6th. What? There's no way. There's no way that's right. Wait a second. There's no way that's right. 162.9 degrees Fahrenheit? Hello? 0.11. I'm gonna do all the multiply things first. 0.11 times 10 to the 6th. This divided by 50 divided by 13.5. Okay, well, we know that the temperature change. I mean, I guess that's fair-ish. 0.9 96 degrees Fahrenheit is the max. So if we get a number that's higher than that, that is incorrect, or if we get that number, that's also incorrect. It should be lower than that. So, okay, we start with equilibrium. Oh, we also got a load. Oh, we also have a load. So it should go up a lot faster. Alright. So equilibrium. We're gonna start with our little moment about, I guess I'll draw a free body diagram. Why not? So we've got some force here. Let's see if it's that way. This one goes, they're both going into the page. So this one is gonna probably want to pull up over here. Wait, why did I? Oh, E doesn't exist there. Wait. Oh, wait, this is interesting. I guess E wouldn't exist there. So it would have to be up to keep it in equilibrium. That is so fascinating. Or I guess, ooh, that's really interesting. I wonder, I think I'm gonna do it as if we don't have a contact there. Because we're kind of trying to figure out the temperature change of the thing. And as we're figuring that out, E is not touching A, B, C. So I think I'm gonna leave it as nothing. But that is very interesting. That is very interesting. Okay, so we're gonna do a moment about B. Positive this way. From statics, everybody loves statics. So minus CD times 200 inches. And then, nope, sorry, positive CD. And then minus, sorry, my brain completely stopped working there for a second. Minus 14 kips, so that's what a K is, 1,000 pounds force. 100 inches. So CD equals, well, so the hundreds will cancel out, it'll be 7 kip. And it's in the CD is being pulled on. It's a tension. So if we draw our free body diagram for CD, we've got CD, and then the internal force, which we can just call like Fi. I don't know. Just call it int. So int equals CD equals 7. Yep. Cool, so we have our internal forces there. For this one, we're not gonna worry about that one. Well, we're not gonna worry about that one because it doesn't have any stress on it. Right, I mean, it has some stress here, but that's not what we're trying to analyze, so we'll figure it out. Okay, so we have our that stuff. Okay, we want to do the deformation type beat. So we want to say delta, the change in this is going to be rho L over E A plus alpha delta T L. So things we know. We know this load, we know the length, we know the elasticity, we know the area, we know alpha. I was just kind of making up that we knew that. I assumed that we knew these things. Okay, yes, and we know the length. We know the length. So the only unknown we have in this is delta T, which is great. We also have delta E, which is just going to be this one. So we're going to have to relate this with some geometry, but we can get this in terms of delta T, and that should be pretty good for us. So this is going to equal, let's see, how many delta T's? So the L of this one is 150 inches, so 150 times 6.5 times 10 to the negative 6. So that is 9.75 to the negative 4th. Delta T. Put that out front because that's where our delta T is going to be, and then we'll add just an additional thing here. So 7. Okay, so in terms of the kip, It's okay because we don't have kip in our this thing. We are in KSI for our E, which is kips per square inch, so we can just do that one. So we'll leave it in 7. So 7 kip times 150 inches over, let's see, 29000 KSI. The K's are going to cancel out. Times our area, which is 1.5 inches squared, so we are chilling. We're going to be in inches. I don't know why I was like, we're going to be in something else. Okay. Equals 9.75 times 10 to the negative 4 delta t plus, all right, 7 times 150 divided by 29,000. This divided by 0.2413, and this is in inches. So we have some amount of change that's definitely going to happen from the deformation that it's experiencing, just from the, getting pulled down on, and then we're going to have this additional temperature change. So if we check, that's a 1.1 inch gap. We might need to have a different temperature. We might need to have a colder temperature, actually. Because one of the things that is actually pretty cool about this subject is that we talked about is if you have a bunch of loads on something, right? Like let's say it's a beam and it's getting pulled down a lot this way. If you bring the temperature down a lot, the beam is actually going to, or this is not great. If you have like a bunch of loads like this way, right? They're kind of pulling the beam out. If we bring the temperature down really, really low, it's actually going to create this thermal load this way on it. And it's going to kind of equalize that out, which is really cool. It's something that you have to, one of the things we're talking about is, one of the things you have to worry about if you're like building a bridge. Because the top of the bridge is like really hot, because the sun, and it's probably sucking up a lot of heat from the materials. And the bottom of the bridge is very, very cool in comparison because it's very shady. So you have like a substantial temperature difference across this material that's going to create a thermal load. So that can actually be he was like, sometimes it's more impactful than the cars actually driving on the bridge, which is pretty crazy, I feel like. Which is not something that you would think about unless you were thinking about materials and other stuff like that. Okay, so we got that. We have to see how much this is going to come down. This is going to be is it going to be the same thing? Not exactly. 13.5. This one is more reactive to temperature than the other one. 13.5. Times 10 to the, -6? I think so, yeah. Times our length, which is 50 inches. So I'm just gonna go ahead and do that out. And I'll put that answer in there. 13.5, whoops, 13.5 times 10 to the -6, times 50. 6.75 to the negative. There we go. Delta T. Alright. Okay, so we got that, we need to have our kinetics now, which is the part that I'm a little bit dreading. So, essentially, it's gonna look something like this, where this angle and this angle are the same. So, they're similar triangles, because of the right angles. So we know that there is some amount of this going on here, and we're trying to set up, so if we say delta CD is to BC as delta E is to AB. so then we can just plug these things in. And what have we got? We got, in that case, we would have 6.75 times, what is our BC? Our BC is 200 inches, so pop a 200 on this. 0.135, so 0.135 delta t, that's kind of nice, is equal to worst number for sure, 9.75 times 10^4 times 100, and then that 2 point whatever also times 100. Okay, so yeah, we're definitely gonna have to thermally like constrict this, because I just got 2.4 for this thing, and that is very large. Delta t plus 2.4137. I don't need that many sig figures. Let's do that. That's fine. So we'll have 0.3 this minus this, which is, oh wait, am I going insane? Wait, is this not that bad? Wait, where am I setting these? Wait a second. Wait. We need to say that E over, oh no, this is more complicated than this, huh? Delta E needs to equal, okay, this is not correct entirely. Oh no, wait, my brain, okay. This is correct, okay, this is not delta E. This is delta, like, delta... I don't know what this is. Like delta CD at E, I guess? Because then we'll say like, oh, this is, I don't actually know if I'm doing this right. Oh, this is a lot of moving pieces. Because the temperature change affects E, and it's going to expand a certain amount. So basically, we want to say like the temperature, we want to say delta E plus delta CD at E needs to equal 0.11. That's what we're trying to say. Now CD at E, the issue is that I'm solving for it now and it's just a number, and that's not good. Because it should depend on delta T, but like there's a thing in there. You know? I don't like that. That's a little odd. Like, it needs to be able to be buffed up by delta T, you know? Oh, wait. Maybe I'm thinking about this the wrong way. Delta CD over BC equals delta CD at E over AB. It wouldn't be equal? Wait, no, it should be equal as similar triangles. I'm thinking really hard. Let me think. It's so close. It's so close. I just need I need a delta T answer for this deformation that's happening at... It's like a ratio, though. Like, so it should be a delta T. It shouldn't be... Wait. Did I just... Oh, I plugged it in instead of... Okay, that's what I did. This does not exist. This doesn't exist. It's just this. This is what it is. This is delta CD at E. Because that was before I renamed it. So it's not equal to delta E at all. So now we just say this. We do this. So we say this 0.0975 delta t plus 6.75 times 10 to the negative 4 delta t plus 2.21 equals 0.11. There we go. 0.11 minus 2.24214. Whatever that is. This plus 6. Where's that number? There. Okay. Now this divided by this. Delta change is negative 23.5 degrees. That sounds pretty close. Metal pipe, thank you very much. Wait, this is literally a metal pipe stream. This is quite literally the metal pipe stream. It's so thematically accurate. This is a metal pipe. Sorry, that was like fascinating to me. I don't know why that like got me so excited. It's like the best time to play metal pipe. Especially because I don't know if I'm gonna get this answer right. I did not get the answer right. What did I do? What did I do? Wait, PEF equals 0? Wait, okay, wait, yes. No, that's fine. I got that right. Okay, I did that too. That's fine. Oh, okay, I feel like I was close. I feel like whatever it was, I was close. I was pretty close. I'm coping. Let me see. Geometry. UA equals, yes, UA over 100. Wait, did I not do over 100? I think I did. Yeah, I did. UA equals 1/2 UCD. Sure. At contact, G minus UA. Yeah. Yeah, I did that right. Did I maybe just plug things in wrong? Okay, that's pretty close. I don't know what I did wrong. Exactly. There might be something wrong in here. But I did most of it right. And I'm happy enough about that. That makes me happy. Under dynamics. This class, I gotta do more for this, but I don't have a quiz on this till next week, so I can put it off a little bit. You know how it is. And by a little bit, I mean, oh, you know, smiles, winks. Where's my oh god, complete quiz on, oh, I see. Homework 1, Introduction to Resistors. Oh, I just did that one today. Lol, I need to do this as well. I'm gonna pull that up. Sorry, I'm just like looking through my this shit. Okay. Curvilinear. Let's go. Let's do it. Let's go for it. Okay. Oh boy. What is this? What are these things? What is this? Oh, that was for Sexy A. I put that in as a reminder, but I already started that CE to Twitter. Okay. Homework 2. We're winning. Okay, I do have to like blow this up. Oh no. Okay, can I like, oh god, why did I do that? A normal scuffed damie stream. That's what you come here for, right? Okay. Here we go. Alright, first question. 2 model rockets are fired simultaneously from a ledge and follow the trajectories shown. Neglecting air resistance, which of the rockets will hit the ground first? Okay. So they're fired simultaneously from a ledge. Let me think. The answer depends on H? Why is this so complicated? Oh god. Projectile motion. Me trying to remember in the back of my brain. Me furiously Googling projectile motion. I don't remember projectile motion that well. No, I do. I just, like, don't... I have not done it in a long time. I remember... But it's asking about the time it takes to hit the ground. So... You can do that with... X, right? No, X is constant velocity. Let me remember. X is the constant velocity part, and you can use that to figure out, like... You can use that to figure out the time stuff, can't you? Because, so Vx equals... Vx is constant. And, you know, Vx equals, or x equals Vxt. So... I mean, I don't know if they're fired at the same speed. Can I figure that out? Do I know? Let's see, we don't know time. We certainly don't know time. We do know x. We are not given velocity. We're not given velocity here either. We know acceleration. This is too many unknowns. That's like 3 unknowns. I think you might have to assume that their velocities are the same. Or maybe I'm just dumb. Maybe I'm just silly. Maybe I'm a silly guy. Let's see. X equals Vxt. If their velocities are the same, then the longer distance would be the longer time. I'm gonna say that if V is the same, longer x is longer time. That would mean B. Now, is that right? Debatable. It's been a while since I've done projectile motion. What is a projectile? The physics classroom. Let's see. Let me see. Maybe they have something. I remember doing this. Nope, that's not it. It doesn't have to. I feel like it has to do a lot with, like, the initial speed of the stuff. Do you think I could help you understand this problem better by firing me off a ledge? If we both got fired off the ledge, then it would help me understand this problem better, because then one of us could do this one and the other one of us could do this one. But if it was just me, then, like, I couldn't compare it to anything, you know? I need, like, these comparative velocity ones. Projectile motion... GIF? What is projectile motion GIF? Animated projectile motion GIF. Me and Clem off of it? Sure. Oh, guys, look at this. Oh! Okay, don't listen to that. I didn't do that. This GIF made me, like, scared, though. Wait. I don't want to add a new thing. Wait, go to full screen. Full screen. Let me show you this thing that made me do that. Look at this. It was fine, and then that's so scary. I don't know why I did that. That was really scary. It jump scared me. Why can't I not? Oh wait. Huh? It's just a guy throwing a stick figure throwing the same ball over and over again. I don't know. I don't think they hit the ground at the same time. For various reasons, but I could literally have so much egg on my face right now, you guys could be like, haha, you cat boy, you silly cat boy. I feel like if the velocity is the same and you're going a farther distance, your time has to be longer. Wait, I forgot about acceleration. You know what, I'm not gonna think about that one. Let's just pretend that it doesn't exist. Everything will get better if you just forget about your problems. You know? Classic technique. Where did my dynamics go? Where did it go? Oh, here it is. Oh no, where did it go? Okay, there we go. Oh no, we have not escaped that. This should be the easy part. Why is the derivatives gonna be the easier part for me? This is like high school review. Okay, it's been a while since I've been in high school, I'm not gonna lie. Okay. Ball A is thrown straight up, just like me. Which of the following statements about the ball are true at the highest point in its path? Okay, easy. Okay, the velocity and acceleration are both 0. Incorrect. This is not 0. Okay, well, I really didn't draw it right, huh? The velocity is 0. The acceleration is not 0. The velocity is not 0. There we go. That's something I can answer. Acceleration is gravity, but velocity changes because it goes up, and then it goes over. Negative. I do know that one. If I didn't know that one, I would be a little worried. I think if I posted, you know that post that's like, oh, what tweet would you do? So like if you were in danger. If I posted, guys, the acceleration at the top of projectile motion is 0, then you should be worried. That's not me. Somebody got me. That would be a scary day. Okay. Ball A is thrown straight up with an initial speed of v initial and reaches a maximum elevation of h before falling back down. When A reaches its maximum elevation, a second ball is thrown straight upward with the same initial speed. At what height y will the balls cross paths? Well, that's a great question. Okay, well, let's just think about, like, some things here. When you throw it up, it's going to take the same time to come back down. So this is t, and this is t. Right? Second ball is thrown straight up with the same initial speed. So if this second ball is getting thrown here, it could not reach at h. That's impossible, because this one's already started falling. So it definitely can't do that. And it's also not going to be 0, because that would be, like, weird. Now, if I throw this, and I just draw it, which means nothing. That means nothing. And I just drew something that just doesn't, like, actually approximate a parabola. Well, what we could say is, like, we could say that, we know that the ball is going to cross at... It's not a linear thing of it going up, right? So it's gonna be moving faster and then moving slower. What else do we know? What else can I try and worm my way out of thinking about this problem and doing math for it? Okay, so we know that I think it's probably pretty unlikely it would be B, but that's not a good way to do this problem. We know that it's gonna hit its maximum elevation here, right? When this hits the ground, it's gonna have done its thing, which, you know, doesn't mean anything. That's when it's there. It's gonna, because the time is the same, and, you know, we're assuming that, like, the wind doesn't, like, blow by and change everything. h/2 is not gonna happen, I will say, because they're not lines, so we know that it's not gonna be that. Now, I feel like, okay, let me write not lines, just so she knows that I didn't do it based off of this picture. Not lines, too high, too low. Now, okay, let's think about this. It's gonna take its sweet time coming down, and it's gonna pick up speed. The first ball. The second ball is getting speed and falling down. It's gonna, so we have one that's picking up speed, to use an animation timing chart here. One that's picking up speed, the other one that's picked up speed, that's losing that speed. Maybe it would be at h over 2. Grr. What would it be? What would it be? Okay, h over 2. It can't be h over 2. It can't be h over 2 because it's a parabola. It's a parabola. What is it? What is the equation for projectile motion? 3 physics equations. Sighs very deeply. Okay, we know acceleration, we want to know time, we don't know placement. VVO, I guess? Wait, we want to know height. Did I say that? We don't know... We know acceleration. We don't know time. We know velocity, kind of, and we want to know height. VO plus AT. Okay, so one of them, delta x, equals, like the position of x equals its initial velocity 0. So it's 1/2 gt squared. What if I just graphed it on graphing calculator? Sorry, I shouldn't do that. The other one is VO plus 1/2 gt squared. And we're trying to set these equal to each other. VO equals 0. Okay, that's not right. VOT? It's VOT. I don't know T though. The time that they intersect. I don't really care about the time. Wait, wait, what? Wait, what about VO is 1/2 delta, wait, let's try this one. Hold on. Okay, then I just switched over to my mix it up. That was not what I wanted to do. Okay, wait a second. So V squared equals VO squared plus 2g delta x. We want to say that we want to say they're equal. My tracking is broken. There we go. We want to say they're equal, but this has to be like height minus delta x for this one. Okay, so v squared equals, but I don't care about v, is 0 plus 2g, let's say h minus delta x. And the other one is going to be v squared, which is, I don't know what the velocity is. They aren't the same velocity though, so I feel like this is also a dead end. The time is me saying, I used the right equation. The physics is winning, guys. The high school physics is beating me. The high school physics is beating me. This one, I'm not beating the silly Capillary allocations. Okay, 1/2 g t squared. I don't know when t is. Oh, but we can set t equal to t. Oh, that's how we do it. Maybe h minus delta x, and then I think we're chilling. And then we have delta x equals... Is that... Don't worry about it. Is that right? VOT plus 1/2 GT. Oh my god, it's gonna be an... Oh, it's gonna be a thing though, is the issue. What if I just set x equal to each other? I need to find x. I'm just gonna say b. I'm just gonna say b. And that's what we're gonna come back to. I'm just gonna say b, and I'm gonna graph them later. And that's how we're gonna figure that out. Two cars are approaching an intersection at constant speeds, as shown. What velocity will car B appear to have in an observer in car A? Well, car is moving this way, but A is moving this way, so you add these two together, I think. This one. Put it in red. The only logical thing I can think. I mean, it's not super logical, because I feel like if you looked at the car, then you would know that it was that. Okay, I don't know. That seems weird, but we're gonna go with B? That's fine. I'm fine with that. Oh my god, there's more conceptual things. Please let me get to a normal one that I feel good about doing, because these conceptual ones are kind of kicking my ass. I'm not beating the non-conceptual. Okay. Blocks A and B are released from rest in the positions shown. Neglecting friction of all surfaces, which figure below best indicates the acceleration, direction of the acceleration of block B? Oh boy. I feel like this should be D. This one? Oh, it's below me and coming towards me? Oh, this one? Low velocity. Wait, which one is car B? Oh, my bad. Let me zoom in. Oh my god, that's so hard to see. Wait a second. Which one is B? I didn't even check. I just thought the top one was gonna be B for some reason. I don't know why. Let me see. I've zoomed in as far as I can possibly zoom in. I for some reason thought it was the red car that was A. It kind of looks like this is A. Oh, no creep. Okay, yeah. It kind of looks like A, and this is B? I don't actually know. It's below me and coming towards me. If it was that one, then I think it would be... Wait. Then I think it would be... Wait. Wait a second. Well, either way I add them. Left car is A. Yes. Yeah. What speed does B have? Well, I mean, wouldn't you just look at it and wouldn't you just see it? I think if you're just... I think it might just be adding the vectors. I'm not sure if that's correct, though. I could be very wrong. But it's like, if you're moving to the right... The only other thing I could think is... Maybe it's the other way. Maybe it's E instead. Because if you're moving to the right... and you're looking here... and it's coming forward... you might think it's going this way? You know what I mean? Like, if you're... this is you. Like that one, that one... what's it called? Umbrella Academy meme. I don't know. It's kind of a weird question. Yeah, I can argue for E. Yeah, I think it might be E, actually. Because the car isn't gonna look like it's driving this way if it's coming forward. But I feel like this is also like... a human being would know that the car is not driving that way. I think it might be E. Rewrite B. E. You can tell that. It's kind of weird though, huh? I think I vaguely remember this from like talking about reference frames and superposition and stuff. Of like time dilation. Actually, not even that, like quantum physics stuff. But maybe... this is weird, this is a weird one. Not sure how I feel about that one. This one though, I do know that like one of the accelerations is going to be gravity. That's an acceleration. And it's because it has a component in this direction that it's going to move in this direction. So I think it might just be gravity. Funky question? I agree. I think the thing with this question is most people assume, oh, well, you have an acceleration, you know, the block is speeding up this way, and so it has to be from, you know, this direction there's an acceleration, but that's not That's not it, I don't think. But I don't know if you would have... It's definitely not just this. And it's definitely not that. I don't really see what you could do to make it that. I mean, that would be like if you had acceleration in this direction and acceleration due to gravity. But they're released from rest, so the only force acting on them is gravity, and we're neglecting friction. So F equals ma. But the very off to the side. F equals ma. Our acceleration is based off of our forces, and we only have gravity. So I think it's only only down, I think. Not too sure. I think it's that. That like makes sense to me. But then again, you know, sometimes these things don't make that much sense, and you think you know what you're doing, and then you don't. But that's okay. That's why we practice. Okay, let's see. Finally a math question. Thank God. Saving my ass. Doing the math. Not the high school physics I haven't looked at. Alright. Alright. Yes. Yes. Yippee. Okay. We got motion of a particle in parametric. But, you can also express this in vector form. I mean, it is vector form, but you can, yeah. Sketch the path of the particle in a time interval, 0 to 2 pi. Okay. We can do that. Alright, let's do a long boy. 2 pi. Pi in here. We got pi over 2. Pi over 2. Probably pi over 4. Kind of inefficient way of doing this, but it's okay. 7 pi over 4. Alright. We got some pi's up in here. Alright, so x is going to be that, and y is going to be that. So I'm going to sketch the graphs of those first. So let's do y is going to be a little easier. So this is y and this is t. So 10 minus, so we start at like a baseline sort of 10, and we do minus, can I explain propagation delay? Ooh, I don't know if I can. I don't know what that is. Not sure about that one. Oops. Let me open my ball. Let me see. I can do a little look-see. Take a little look-see. Let me turn on my light first. My camera is just not working. Oh, old man noises. I'm sitting down in my chair. Okay. Propagation delay, huh? Let's see. Propagation delay. How do you calculate latency? Oh. Oh, this looks like, ooh, circuit stuff. I think the class before me is talking about this. Let's see. Yeah. Time duration taken for a signal to reach its destination. How do you calculate latency? I would assume there's a formula for that. Subtract the start time from the end time. That makes sense. That one I can't understand. Just it's how long it takes for it to receive and like react to the signal versus the time you sent it. So you would take the end time and you would subtract the start time. Okay, 5 cosine t. So if we're doing minus 5 cosine t, that means our lowest would be at 5. So we're constrained between 5. And we kind of start at, cosine starts at 1, so we would start here, Here we go. This. This is at 2 pi. So if you segment the packets, it takes time to put the segment packet into the link. I'm not too familiar, but I do know that, like, from my very introductory information about like Wi-Fi and sending packets and transmitting that kind of data, is that like if you're segmenting stuff, it takes time to put it back together. That's transmission rate? I don't know if it would... I don't know what you mean into the link. I would assume anything would take time to sort of send. This is T. Oh, wait. Oh, oopsies. This is not... This is in T. That's YT. Link the bridge from one end to another. This one's gonna be in like 1, 2, 3, hopefully. I don't know, I'm gonna leave it like that. This will be X though. Shit. Oh wait, I might want to substitute this actually. If I saw, that's kind of nasty, isn't it? It's kind of nasty, isn't it? Just sketch the particle of the path for time interval 0 to 2 pi. How does segmentation fault happen in the array? Can I explain it? No, I don't know that one. I don't know what a segmentation fault is, actually. Not too sure about that one. I've never done Wi-Fi stuff at all, but it's very cool. Like, the most I know about it is more about the sort of technical optics side of things, which is less about the programming. Okay, this one, I'm trying to think. Maybe it would be better if I did some derivatives. Because I know we can do like dx dt, dy dt. We can get dy dx. I don't know if that's like fun. I don't know if that's like a good move, you know? Fun is... it's always fun. I don't know if that's a useful move. What was my project in my network programming class? I did not take a network programming class. I took an introductory computer science course where we talked about networks. I mean, my dad is in software, so I know like about some web stuff like that's not like from classes, and I also just like taught myself a lot of code, but I am not a CS major. I definitely don't know that much back-end stuff. I dealt a lot with like fun front-end things, like making video games and doing HTML and some Node.js stuff and learning PHP briefly. Okay, I want to think about like the best way to like tackle this before I just start jumping into stuff. So I can do like for a certain T. I guess. Did you learn system call in operating system? Nope. I do not know that one. I guess I kind of want to say that this is X. Okay, let's do this. This is X and this is Y. I'm gonna get rid of this. I don't know. Let me sketch X first. Because I think I can say like, okay, for T equals this thing, what does X equal? What does Y equal? You know? It's not gonna be this, though. Like, Y is ranging from 5 to 10. So, break. We'll do a little break here. 5 to 10. 6, 7, 8, 9. Yeah. It's maybe not the most ideal way of doing this, but... my X is so huge now. Okay, I'm gonna shrink it a little bit. Redrawing this. There we go. Should probably be a little bit better. I don't know what. Get out of here. Now you just gotta delete it and you gotta start over. Sad but true. 6, 7, 8, 9, 10. Oops. There. It's y. And then for x, we have 10t minus 5. So that's like this line. Here, we'll say this is 10. Oh boy. So, like, well, this is our kind of guideline. We have 10t minus 5 sine t. Sine t starts at 0. And let's put 2 pi in here. So for 2 pi, this would be 20 pi. And so it would be like if we had minus 1. Well, so sine is going to get bigger. Like that. Like, it's, I guess it's kind of like... How do I do this? Okay, so for t equals pi, that's also 0, I think, right? Yeah? Yeah. And then in these intervals, we have, when it equals 1, we go to 10t minus 5. It's always going to be a defined distance below it, so like somewhere here, I guess? Like that, sort of? But it would be like... When is it negative? Sine is negative on... It would be like... That? That's crazy. Is that right? I'm gonna go to Desmos. I feel like that's a little funky. Minus, what was it, sine x? Oops, okay. Maybe not. Nope, it just looks like a line. That's weird. Oh wait, minus 5 sine x. It does kind of look like a wibbly wobbly line. It's not very wibbly wobbly, but it's a little wibbly wobbly. Wow, that's crazy. What if we did like 10 sine x? Then it would be very wibbly wobbly. What about 8 sine x? Wow, that's so cool. What about 100 sine x? Okay, that looks like weird. What about like 20 sine x? That is so fascinating. The more you know. Okay, so it doesn't look exactly like that, but like just pretend it kind of looks like that. It's a little bit more like this. Or like up, and then, yeah. Okay, none of these are entirely helpful to me. But when t equals 0, let's see, what do we have? This is gonna be somewhere between, like, I don't know, 5 and... What is 20 times pi? Like, 60-ish? Let's go with 60-ish. Wait, 20 times pi is gonna be more than that, isn't it? Might be 20, better 65? Yeah, 60, we'll do... No, 60 is close enough. Okay, maybe we do 10. 20, 30, 40, 50. Okay. Okay, so for t equals 0, we have 5 and 0. So here. No, here. Oh boy. Okay, so that's t equals 0. Then for t equals pi over 2, we would have 10. And for t equals pi over 2, t equals... Oh god, okay, let me do this. So for t equals 0, we have x equals 0. Y equals, not 0, equals 5. T equals pi over 2. We have let's see, so for pi over 2, that's up. That would mean that x is, I guess, 5 pi minus 1, minus 5. And y equals 10. 5 pi minus 5, what is that roughly? 10.7. It's like kind of 10. Like there. T equals pi. We would have x equals 10 pi. 10 pi, and then y equals... Okay, that's a negative number, so that'd be actually 15. Gosh darn it, I didn't get a 15 in here. Now if I put there a 15 in there. I don't want to redraw it too much. Say that's 10. Close enough. 15. So 10 pi. This is a weird function. Why are we doing this? 31. Like, what is the point of this? Is it like a log kind of thing? Is it gonna spiral? It might spiral. 3 pi over 2. Let's see, x is gonna equal 15 pi. Y is nope, 15 pi minus 5. Y is gonna equal 10, I think, again. Yeah. At least y is like beautiful and kind and nice. Okay. 15 pi minus 5. What? 15 pi. 42-ish. So 42-ish. And that was 10. And then t equals 2 pi. X equals 20 pi. Y equals 5. No. Yes? Maybe? Yeah. Look at my handy dandy graph over here. Okay. 20 pi, that's like the 60, so it would be like here. Ew, that's not where I wanted it to be. It's something. Let's see what it looks like if I try and graph it on Desmos. What is this? I forgot. That's an array. I want to do... I don't remember how to do that thing on Desmos. It's okay. Let's go here. Here we go. Okay, Desmos. We put in... Oh, you guys can't see it. What was it again? I already forgot. It is 10t. So 10t minus 5 cosine t, comma 10 minus sine t. No, switch the sine and cosine. Cosine here. And this one is sine. 0 to 2 pi. Okay, that's kind of what we had. If you change the step to... What did we have it at? 5 to 15. And then on the x-axis was like, yeah, something like that. Oh, it starts at 9? Huh? How does it start at 9? What? What? Am I goofy? I might be a little goofy. 10 minus 5. Oh, whoops, that's 5 plus 2. There we go. Yeah, that looks like not exactly what we had, but close, close. I think it's just because I did a break at the beginning. Yeah, that's pretty close. I'm happy with that. By happy I mean like, you know, it's passable. I could probably do better, for sure. Okay, oh my god, it's been like 2 hours? No way, that's insane. Let's see, let's finish this one, and then I think I'm gonna call it, because I'm like a little goofy. I'm a little like all over the place. And I should probably like go rest my eyes and not look at a screen. Okay, determine the magnitude of the smallest and largest velocities reached by the particle. So we gotta maximize and minimize. And the corresponding times, positions, and directions. Okay. We gotta do some derivatives. Alright. We gotta take, it looks like we wanna do dx dt, so that's a, b, or this is a, I guess, technically. So dx dt is going to equal, what have we got? Let's see, so 10 minus, minus 5 cosine t. And then dy dt is going to equal 5 sine t. So when are these maximized is a great question. They are one of them is maximized. Okay, well, let's do maximized first. Okay, max is this one, is 10. Vx equals 10. This one's max is Vy equals 5, which is when sine is whatever, not whatever, pi over 2 plus k pi. This one is when cosine is nothing, so when cosine is 0, also pi over 2 plus k pi. Which, you know, makes sense. I like that that's, you know, not contradictory. For min, we have Vx equals 5. That's for k pi. And min is Vy equals 0 at k pi as well. So those are the t's, I believe. Corresponding times position, yes, this is t. Equals 15 feet per second. So that's not what we are getting. Unfortunately. Maybe we have to divide them by each other. And then maximize it. I can't just do Vx like that. I feel like I can't. I feel like I definitely can't. Because that's not really Vx. It's not the V component of x. It's like the x component with respect to time, which is like, what is that? That's not right. If I divide them, oh, that would suck though. Well, okay, I guess it wouldn't suck as much. It would be dy dx. So it would be 5 sine t divided by 10 minus 5 cosine t. That also wouldn't get me 15. No. Okay, I might have to think about this more. I might have to solve for t But that, like, just seems like it sucks, is the thing. Like, I don't even know how I could do that on the first one. Do I remember how to do... No, because it's just parametric is like you solve for it, and then you plug it into the other one. And that's how you get it out of there. I mean, I could get the t out of there with, like, an arc cosine, an inverse cosine. It would be y minus 10... Sorry, negative 5y plus 50, and then the inverse cosine of that. And, you know, just slap that in there for t. My favorite equation. That's awful. I don't want to do that. Who's going to take the derivative of cosine inverse? Oh no, the math might be winning on this one. There's got to be something I'm, like, missing about, like, how to do this that, like, is making it too hard to do. Honestly, on both of these, because I feel like this is not this way is not the most efficient way to do it, and I feel like this is a train wreck of something. But it's like the 15 is so close to, like, the it's like these are added, you know, it's so close that I feel like I'm really close. I'm almost there. Oh wait. No, wait, what? Wait. Vx equals 15 feet per second? Wait. Wait, what? Wait! They're right! She's right, it's not that, it can be positive. It can be 15 here. It can be 15, and that's what is it? It's at negative pi, I think. Is that right? Or no, not well, I mean technically negative pi, but I think it's just pi plus k pi. Because it's on that side plus 2k pi, wouldn't it be? Yeah, because there's only one place. 2 pi k. 2k pi, k2 pi, whatever. And then I guess the idea is that, like, this and this would go together. So, this is the max out of this. This beats out this, so this is whatever, who cares? And this is the min, so this would be this. And it would have to be on k pi plus 2 pi. It would have to be pi with 0. It would have 2k pi, 2 pi k. Because I can't get rid of the... This is weird. I don't know what that is. Oh, I do know. It's not the periodicity. Okay, this was kind of scuffed, but thank you guys for hanging out, if you hang out. I'm gonna try and... I don't know. I'm really close to my mic now. I want to figure out better times to stream. I don't know. I've been messing around with stream times, just so that everybody can be here, and it also works for me. But I have less lion dance practices now instead of 3 times a week. Well, no, I'm about to have more, but but not for me running them, so it's okay. Yeah, I'm just gonna end it now. I'm gonna go eat something. I hope everybody has a nice day. I'm probably gonna be live. So the thing is, like, I don't know what I'll have to do, so I know I have this. This is, like, I'm supposed to do this by, and I know it's so funny, I feel like I never mentioned this, but it's like, when should I stream so I can do my homework on stream? This is on Friday. So, I have practice... I might be able to stream Thursday... No. Maybe, no, I can stream Thursday. My practice is until... No, I have practice Thursday. Maybe I'll stream on Friday. That seems like a good idea. Streaming on Friday when it's due. So it'll be either that or, you know, I'll do this other one that we have, which is relative motion. That's probably more likely. Lots of dynamic stuff to do. So yeah, I think that's it. Hope everybody has a nice day, and I will catch you later. Bye.